you have your delta yet? Okay. The scratch work again is to your benefit, to as much or as little as you like. The proof will be everything shown. All right, now do you have your delta? 2 epsilon. Yeah. Delta is 2 epsilon, you're on your way. This more than most topics is so easy to just get lost in the symbol question. I can do it. I don't know what the hell I'm doing, but I can do it. Remember the whole idea is you're trying to show that for any arbitrary closeness you can get as close to the line as you want. Now it looks like a lot of theory and symbol questions, but that is the idea. Okay, boom. How do we do? All right. I will, oh, doggone it. You got me. I lose. Jordan Radley pointed out that you should probably identify what the heck f of x stands for. I continuously forget that. That's the kind of thing that would probably cost me points for a student. There is no f of x named in your problem, so you should probably tell the person what the heck. Okay, what? You name it g of x, you name it George of x, whatever you want. Okay? Now, here's the deal. Cool. Let's talk slope fields. Now, I did a bang-up job of teaching this. I feel like people could do it. But at the end of the day, at the end of the lesson, my own daughter said, okay, great, so what's the point? What can you do with this, all right? And I had to struggle a little bit, but eventually I came up with this. Do you agree that when you're in a car, the most obvious readout is your velocity, your rate of change? Not necessarily your position, because it tells you how far you went without in any one direction, right? So the velocity is the main sense. Now, it is often the case that you know, in real life, physics especially, but in real life, you know a rate of change, but not the original thing. So for example, if I got in the car while you were driving, God help me, and I recorded, I just looked over and looked at the velocity after every couple of seconds. I could say that the velocity at time 0 was 0, and at time 2 was 50 miles an hour. Probably not that. That would be really fast acceleration, maybe 20 miles an hour. And I could continuously find points and register points, right? Are you with me? Now, if I then wanted to write an equation for the velocity, my main objective would be to try and get as close as I could to the points. That's modeling. When you do mathematical model, in which if you go on to be an applied mathematician, that is a big part of their job. Modeling some kind of real life data through some kind of mathematical function, an equation. Hopefully based on prior knowledge of what it's supposed to look like. But my point is this: when you're modeling, you're just shooting for an equation that matches the data pretty well. What you're not trying to hit is an equation that can be easily integrated. Now, that's a bummer then, because if you wanted a position graph, you're not going to necessarily be able to integrate your model. It could be a big stinking mess that you used all these different combinations of functions to get it to match this cube, but then approaching an asymptote behavior. This would require you to draw on a couple different function ideas, even a piecewise or something like that. So it wouldn't necessarily be integrable. Yet, by knowing the rates of change at certain points, I can actually make what's called a slope field and say, well, based on how it was changing here, the slope would be this and that. It would be 20 miles per hour, then 40 miles per hour, then 30 miles per 40 miles per hour, then 30 miles per hour, and so on. So I could get a look at what the position graph was like, even though I couldn't even integrate it. That's where we're headed, all right? Now, that's the use of slope fields. Unfortunately, this equation would be really complicated. And it's hard to learn slope fields on a really complicated equation. So the equations I'm going to do to start with are going to be pretty clean. But just know the point of this is usually to deal with functions you can integrate, all right? So check this out. If I asked you to find and graph the general solutions to dy dx equals 2x, what is the general solution on paper? Y equals, actually I'll split the differentials. dy dx is 2x dx, so y is x squared plus c. Now, analytically, there's one general solution. Graphically, there are many general solutions. All the possibilities of different parabolas that had a different constant that went away when I took the derivative. So we have all these possible derivatives. 1, 2, 3 over 1. There's the basic, oh no, I missed. There's one. And here's another one. And there's another one. It should not overlap ever if I do this well, but who's to say I'll do it well? 2, 3. Okay, my point is we get a whole family of graphs, right? You got this trick, 100% with you. Thank you. All right, ooh, this is going to come out so pretty. I bet you wish you had all these colors. Huh? All right, a little. Yeah. All right. At any rate, there. Oh, now I'm going to use a heavy one. Whatever. At any point, if they gave you an initial condition, then that would allow you to nail it down to one possible curve. So imagine they told you, yeah, it's that differential equation, but it also has to pass through the point 2, -1. Now, the only way you're going to do that is with one equation. So if you make 2, -1 a heavy line, then that would be the particular solution. Coolio? Cool. Now, we knew the slope was y equals x squared, or the shape was y equals x squared because we integrated. And yet, I could get possible shapes without integrating it just by saying, well, based on different x's, the slope would be actual numbers. At 0, for example, the slope would have to be 0, okay? And so on. Now, that's the idea of a slope field. A slope field is like a dot to dot, I suppose, but instead it's little tiny segments. It goes a little something like this. If, instead of integrating, I just made little slope calculations. Now, when x is 0, if dy dx is still 2x, then what's the slope? At any x equals 0. 0, right? Because 2 times 0 is 0. Now, in terms of the slope field, then, here you go. At x equals 0, let's say I go to the origin. That's where x equals 0. The slope is 0. Now, I am going to make the most minuscule little baby slope there. Now, you make it really small because making it large would be a lie. The minute I went to, 1/3 or something, is the slope 0 anymore? If I'm at x of 1/3, now the slope is 2/3. So you make it as small as possible just to say at that little instant the slope is 0, and really not once you're off of that much. And wouldn't it be 0 at any place x equals 0? So I could draw little baby slopes everywhere x is 0. What if x was 1? Then what's the slope? 2. All right, now let me give you a little pointer. It's hard to make your slopes look different. You'll see in a second here. Here's what I want you to do technique-wise. When you go to make your new slopes, go to a point where x equals 1. Obviously, there are a lot, but let's go to an obvious one like this. I think you'll agree x equals 1. Yeah? Put your pencil there. Now, in terms of how steep to make the slope, you imagine a point that is up 2 over 1 away. If I went up 2 over 1 away, I want to point in the direction of that guy. So imagine trying to put your pencil here and point to that guy. It might look something like that. Now, the minute you have that slope, then everywhere above and below it, you can just try and match that slope. Up 2 over 1 from there, up 2 over 1 from there, up 2 over 1 from there, up 2 over 1 from there. They should all be parallel. Same steepness, yeah? Then the table has served its purpose. You never make a table. I just wanted to introduce the idea. When x equals 2, then, what's the slope going to be? 4, all right? So if you imagine a point that's up 4 over 1, it should definitely be steeper than the one next to it. It doesn't, I'm not going to look at that little slope and say, that's not 4. I do look at it next to it, the one left of it, and say, relative to that one, it looks wrong because it needs to be steeper. Right? And at 3, it's doggone near, it's just past vertical, almost vertical, but not quite. Are you with me? What about a negative one? -2. So put your pen on a point and imagine a point down 2 over 1 away, and then continue to do that. Okay, now that's slope field. This should typically then be used to nail down what the graph of the antiderivative looked like. Like when we knew the rate of change of the velocity, we wanted to nail down the position here. These are rates of change on the original function. So these should be little slopes on the original function's curve, the original y equal x curve, right? This is not the graph of the derivative. The graph of the derivative obviously would be y equals 2x. This is a picture of what the slopes of the original function were like. Now, depending on what point it must have gone through, the curve could be a whole family of curves like we saw before. Now, if they tell you, yeah, the graph of the slopes looks like that, now draw a curve through negative 2, 1. If I also told you that the original curve has that slope kind of idea of the curves, but it also passes through negative 2, 1, now I can actually get a decent sketch, not nailed, a decent sketch of what the curve looks like. Now, this, for example, what's the slope at negative 2, 1? Negative 2, at negative 2, it's negative 4, right? Now, people want to then say, all right, so I go from here, I go down 1, 2, 3, 4, over 1. Boom. And I understand, but what's wrong with that? Okay, yeah, it's not, do you agree there's some 2.5 here, or negative 3 halves here, yeah? What's the slope of negative 3 halves? It's not negative 4. It's negative. At x equals negative 3 halves, the slope is negative 3. So the minute you go off that point, the slope's not going to stay negative 4. It's going to start to be a little less. So you don't do a little dot to dot. Just like if I said, hey, graph a parabola, you wouldn't say, it's this. It's smooth, okay? Now, there's going to be some gray area here. Your estimation of where the slopes go, you might say, it's going to be a lot like, it's get a little less steep. Well, it's about negative 2 there, so that's about, and then it needs to get flatter. And then once it gets flatter, what does it do on this side? It needs to start increasing and then get steeper and steeper and steeper. Now, yours then might be a shape like that with a y-intercept of negative 2 or something. The next person might have a y-intercept of negative 3. Nobody's going to care about that, okay? That you have the shape correct. That's the idea. They're not going to get point-by-point specific. You just can't know that without doing lots of slopes between the integers, and we just don't do it. Okay, you with me so far? Now this then is the actual y graph. The slopes are possibilities of how the graph slopes at different points, but once they give me a point, I can kind of get in a rough sketch of what the graph looks like. Boom! You go. You go. This will take a while the first day, but this will go quicker and quicker. You'll start cranking these out. But it is kind of learn some techniques and some shortcuts. Feel free to talk it over with your math amigos. Disagree? Like I said, you'll get better. You'll be faster than everyone's quizzing. Good luck. Yes, sir.
On this one, slope is 0, why are they signs are upward like that?
At x equals 0?
Yeah, alright.
At y equals 0?
Yeah.
Because if y equals 0, the slope would be 2 minus 0, so 2. So shouldn't the slope be 2?
How do you decide which direction? Is it a positive?
Oh, what's the slope of 2 is up to right. So it's back 1, 2.
So you still do the slope in terms of x?
Yes. The slope is still, yeah.
That's what I was just using.
Last one is a bit of a humdinger. Okay. All right, how we doing, people? Ooh. Are we getting there? All righty, a little bit of thought process here, okay? It's pretty common that when you have a slope that is undefined, that you don't really show anything. That said there, okay, I can't put in x equals 0 and calculate the slope. But what if I put in a 10th? We don't usually draw slopes at the fractional or the between the integers points, but what if I put in the slope at a 10th? What is it? 10. So there is curve here. It's practically vertical, yeah? Now that said then, that if you get no slope at x equals 0, then you should think either vertical asymptote or vertical tangent. Could be one or the other. It's possible that there's not a vertical tangent there. Think of a circle, for example. There's not a vertical asymptote at this point, but there is a vertical tangent. So either one of those could be represented. All right? This guy, you can see that the easiest place to go to start with are slopes are 0. Slopes are 0 when what? When y is 2. You might have also noticed that the slopes are all the same vertically in this first one. Why is that? Once I found a slope at x equal 1, it's the same everywhere. Why? Because what? Yeah, look at the equation. dy dx depends on x only, okay? It doesn't matter what the y is. When y is 2, the slope is the same. When y is 5, the slope is the same. And so you can see that if the differential equation depends on x, then the slopes will all be the same vertically. If the differential equation depends on y, then the slopes are all the same horizontally. X doesn't matter, all right? It depends on y, so it changes with y, so it changes vertically. This is going to change both horizontally, you can see it does change horizontally, and it changes vertically. And that's because the differential equation depends on x and y. All right, what is this graph? Yeah, it's a hyperbola. If I gave you an initial condition over here, it might be a sideways opening hyperbola. If I gave you an initial condition up here, then it might be a vertically opening hyperbola. Those types of hyperbolas both have the same differential equation. All right, let's go to the other way around. Now, the AB free response almost always has a slope component, but the BC not as often. You guys are more likely to have to do multiple choice or matching kind of differential equation. Now that goes to a little bit of thinking. There's some tools I can give you. Would you please go to the bottom and write down some things you might use to match? Because to the uninformed, it might look, oh my gosh, there's slopes all over the place. All right? The very first thing I would do is what I would consider the easiest place to start looking is to look for whether it's 0 slopes or no slopes. For example, this, dy dx equals x minus 1. This would have 0 slopes. 0 slopes when what? When would this derivative come out 0? When y equals x. Anywhere along y equals x, you should have 0 slope. Look at this graph. Along y equals x, does this have 0 slope? Not so much. This guy, not so much. Look at this one. Along y equals x, all the slopes are 0. That's a candidate. Okay? This guy, the slopes are not 0 along here, so that's not it. That's not it. That's not it. Those are not 0 slopes. That's not it. What about this one? Yeah, that's also a candidate. Slope field A is a possible candidate because it also has slopes of 0. That right there, that technique alone limits it down to slope field 3 or, what was the other one? 8? What was the other one? 8. Yeah? Are you with me? Okay. Sometimes then, once you can get it down to 2, you can then choose by going point by point. I probably have these in the wrong order. Just by choosing a point, if, say I chose, what about the point 1, 0? If I put 1, 0 into that equation, what's the slope? 1. Okay, the slope is 1. Now, which of those two choices at 1, 0 has a slope of 1? This guy looks like it has a slope of 1. Slope field 3 does. But slope field 8 looks like at 1, 0 it has a slope of -1. That's a no. All right? So just by choosing a point after you've narrowed it down, you can go with slope field 3. Are you with me? All right? next thing I think I would probably go to is this idea. I do these, all these things go through my mind, so I don't know if they're in priorities. Another thing I might talk about is if the slope does not change vertically. If the slope does not change vertically, then what does that imply about the differential equation? Should it depend on x only or y only? If it doesn't change vertically, it doesn't depend on y. So dy dx depends on x only. So say, for example, this guy. Actually, let's go this guy. Differential equation 7 depends on y only. So it should, I just went. If it depends on y only, then it should change with y, not x. So if I'm looking for the slope field for this, I should look for one that stays the same going side to side but changes vertically. This stays the same side to side but changes vertically, so that's a possibility. This changes side to side. This changes or stays the same side to side but changes vertically, so that's a possibility. Those are good possibilities. And after that, I could choose based on the zero slope idea. Where would this have zero slope, and y is 0? So I should have zero slopes at y equals 0. That must be slope field 4. You follow? Next, let's go to 3, quadrant signs. For example, if I looked at that differential equation 2, is x over y. This is handy when the slopes are changing all over the place, x and y, okay? What are the signs of the slope? If that's the differential equation, what are the slope signs in the first quadrant? Positive, right? In the second quadrant, you'd have negative x's, positive y's. What's the slopes sign? Negative, positive, negative. So for matching differential equation 2, you would look for something with positive slopes here, negative slopes here, positive slopes here, negative slopes there. You also might use the fact that we just did that problem on the previous. But what works there is something like, I didn't mean to mark this out. I'm feeling like something like a slope field 6, yeah? Are you with me? Positive slopes. I think that's the only candidate that I'm looking at that's verifiable. Okay, so I feel slope field 6 is the correct one. Check. Last but not least, again, I apologize. I know you want to just crank these out, but last technique is if the antiderivative is known, that's really easy. Look at differential equation 5. What's the original equation? If the derivative is x, then the original equation must have been x squared. Which of those, if you drew graphs over it, connected the dots, which would look like parabolas? That's a good one. That's definitely not parabolas. That's not parabolas. That's got a crazy thing going on here. So that would tell you right away that differential equation 5 must be slope field 1. All right, that's enough me up and match them all, and we'll go over them in a minute. All right, sorry I'm slower than most. Okay, did you get something like 3, 6, 8, 5, 1, 7, 4, 10, and 2, 9? Yay, okay, that is a good introduction to slow students. Now it's just practice. All right, 102, maybe we could do 1 or 2 problems off 102. Do you have questions on 102? Yes.
Number 1.
We'll definitely talk, number what?
1.
Yeah, number 1 is a bit of a humdinger.
4.
And 4. One's probably one of the top 5 hardest problems in the book. 13
And 18.
and 18. Okay, cool. Let me at least get you started with 1, and I would have to do 1 tomorrow. All right? Did you get the revenue as a function of number sold and price? Okay. This is not 102? Ah, shucks. I guess I'll have to do that tomorrow. Never mind. 102 number 1, is that, what's that? I don't remember that.
And equal triangles each triangle.
Oh, delightful. Okay. An equilateral triangle, something or other.
Just B, Mr. Rickman.
Just B, okay. Equilateral triangle, square to the radius. Okay, so here we go. It's definitely, there's definitely a better way to think of it than others. I want you to get the radius in here, yeah? Let me draw the radius here and here. Now, isn't the area of that whole triangle equal to 3 times the area of the smaller triangle? Do you agree? Okay. Talk to me about the area of those triangles. Do you want to go base height divided by 2 or 1/2 AB sine C? Base height divided by 2 would kind of stink because I don't know this, yeah? So you should use 1/2 AB sine C. So 3 1/2 AB sine C. What are A and B? With respect to the circle, R. So 3/2 R squared. And what's the angle C? The angle is the angle between the two. So what's that angle? 120, yeah. You took 360, it's an equilateral triangle, it's an equal split. So it's sine of 120. So altogether then, the area of the triangle is, what is the sine of 120? 1/2 or √3/2? 60 degrees is the big angle, so do you get the bigger opposite side or the smaller opposite side? The bigger, so it's √3/2. So it's 3 √3/4 R squared is the area of the triangle. Now that you have a nice clean relationship between the area of the triangle and the radius, you can crank out the rate of change in the triangle, yeah? Got that. Cool. Okay, that's enough, or should we try for 1 more? Yes? We should do 4.
But there's 2.
Is it changed? Oh, that's the one I changed. Is that the,
No, it's changed.
yeah, it's a summation of, aha, okay. Back in the old days, it's been so long. Y equals 2x plus 1 looks like that. Check. You are banned, I say, from using an integral. You must use a Riemann sum, an infinite Riemann sum. So, yeah, you know that this is the same as this. I hope. That's where an integral comes from. It's the infinite sum of rectangles. Yeah? You with me? Okay. So, here we go. Let's start with delta x. Now, normally I would take the region that's 3 wide and divide it into 3 chunks or 10 chunks or 1,000 chunks or n chunks. So delta x is 3 divided into some number of chunks, which I'll let go to infinity. So far, so good. F then would be the height at, so first F would be 1 3 over n. The next height would be 2 3 over n. The height next would be 3 3 over n. So generally, it's F at some multiple of 3 over n. And we would take it from the first rectangle to the last rectangle, which is the end. We'll finish tomorrow. That'll get you started. You probably crank it out now. All right? Finish, or I will be disappointed in you. Again. Sorry. I'm actually always overjoyed and amazed by how bright.
Colorado Mesa University is visiting in counseling. If you're interested, come to counseling.
Have a lovely day. Oh shoot, I just recorded I'm disappointed in you all. That's terrible. That's